Okay, so I'm going to look at then Unit 3, Mechanical Principles, it's called, Principles of Mechanical Engineering. And we're going to look at revision paper. We're going to look at the 2016 paper in a moment, I think it is. I just shown you on the slide there, this is a breakdown of all the topics we've covered in the unit. And they call them learning outcomes to give them their jargon. Learning outcomes 1 through to learning outcomes 5 here. And learning outcome 1 is the one we actually finished with, which was to look at the types of forces, concurrent, non-concurrent forces, and types of loading on mechanical components such as tension, compression loading, shear loading. And that's worth 25% of the test. And then learning outcome 5 at the bottom is the dynamics. That was the looking at the velocity time diagrams, looking at the Newton's laws of motion, looking at the energy methods, potential, kinetic, work done. All that is in learn outcome 5, and that's also 25% of the syllabus. So quite chunky, those two topic areas. Learn outcome 2 relates to geometry, fundamental geometry they call it, 15%, and that's usually centroids. Working out centroids of sections, working out masses of sections, volumes of sections, given densities and so on. So geometrical properties learn outcome 2, and that's 15% coverage in an exam. That's what they're saying they will have. Learn outcome 3 was the levers, pulleys and the gearing that we looked at, and that's 20%. So that was things like type 1, type 2, type 3 levers. That was pulleys and gears. We looked at gear trains and working out velocity ratios of gear trains, gear ratios, that kind of stuff. So learn outcome 4 is understanding properties of beams. That would be working out reactions of beams. That would be working out the bending moments along the beam. That's 15%. That's what we did towards the end of the session. Every paper is broken down into those percentage weightings, all right? So what I was going to do is go through a paper and show you how that breakdown occurs within a paper. This is the May 2016 paper. It's already on our system. If you download it from there, you'll have the paper. I think at the back you've got the answers, and I think the full marking scheme is there from OCR. Okay, I'm just going to go through that paper. Just some points to remember, and this is from the actual OCR paper. Always support your answers with working. In other words, they like to see working, and they will give you marks for the working even if the answer is wrong, because that's quite important. You know, you might be 5 marks for a question and only 1 mark is for the correct answer. The other 4 might be for the working. So even if you've got the final answer wrong, you can still get 4 of the 5 marks because you showed the correct working, but you did something wrong along the way that prevented the answer from being correct. So that's worth remembering. It also does state that even if you get the correct answer, if you haven't shown enough working, you won't get any marks at all. So I'm going to take you through the paper very briefly here, looking at the questions. And I've just highlighted the topic areas and how I would suggest you, go about sort of solving these kind of problems. So question 1 on this paper, it shows you what's called a trapezium shape here. And basically what you've got to do is calculate the coordinates of the centroid of the plate from point A. They've given you point A in the on the shape, and you must calculate your X bar and your Y bar from that position. Okay, so if you go back to what we did in the lesson, we would have had a datum. Their datum is going to be here. They're going to have a datum here, and the datum will be here. All right, this will be their datum positions, and we've got to calculate the location of the centroid, which will sort of down the graph, it'd be somewhere up there, I suggest, somewhere sort of over here, somewhere like that. That will be the centroid of the shape, and we've got to calculate what's called the Y bar, which will be this dimension across here, Y bar, and we've got to calculate the X bar, which will be this dimension here from the datum. All right, that's what we'll be trying to calculate. Okay, now if you remember back in the lessons, we've actually used a tabular approach to solve this. We broke our section down into discrete sections. So I would be suggesting you're going to break it down into a triangle section here. This will be a triangle called, say, section 1, and then our rectangular section will be here, section 2. And then I think we used a little table in the lesson. We had sort of an area, we had a y dimension, and we worked out the area times the y dimension. This kind of little table. If you go back to the revision sheet I've given you, you'll see in the revision sheet and it talks about the sort of structure of the tables and so on we're using. We did this kind of thing, if I remember rightly. We called this, I think we called this the sort of element number 1, element number 2 kind of thing here. So that would be sort of 1, element number 2 in here. And we were working out the area, which we can do for a triangle. We know how to find the area of a triangle. We work out the area of the rectangle, so we can find the areas. The y dimensions are dimensions from the datum. So for the triangle, the y dimension will be to its centroid up here. So sort of the local y dimension would be to there, which you can get from the formula sheet. OCR formula sheet gives you the location of the y bar for a triangle. So we'll work out the y bar for the triangle, the y bar, the y dimension for the rectangle, which of course will be to the centre of the rectangle. And then we can work out what's called the AY values. And what we did, we summated the AY values. So we added them up, so whatever that was, and then we added up the area values, summated them. And then to find the y bar, it was simply the summation of the AYs divided by the summation of the areas, okay, from our table. So in other words, if we use sort of colour coding, it was this value here, and we divided it by this value, whatever that is there. That's how we solved it. Okay, if you remember that, that was the summation of the, that's what I was solving for the y bar. And we do a very similar thing for the x bar. It's just that with the x, we have to use the, obviously the x value. We extend the table here basically, and we have to use the x value, and we calculate the ax value. All right, so again, you do a summation of the ax values in here. Okay, so that's something I would encourage you to engage with, getting back into how to solve for the centroid location for the y bar, and also the centroid location for the x bar. Same kind of approach in both cases, just that we use slightly different values. We're using that value there instead. And there's 5 marks. You can see there's 5 marks associated with that question, so it's really, really worth engaging with this. 5 marks, 24 marks required to pass, and 5 marks on that one question alone. But there's a bit of work in there. Okay, so I'm going to leave that with you. That's just a sort of little prompt to get you focused on what you need to do there to calculate the x and the y bar. But I want you to engage with the process and get back into how you evaluate centroids. Okay, so I'm going to leave that one with you there. Given in part B of question 1, 3 forces that are acting on the structure. So the forces are shown here. If I highlight them in red, that's a force there of 20 kilonewtons, showing at some kind of angle there. We've got a force of 12 kilonewtons, applied at D, that was applied at C, and we've got a force here of 5 kilonewtons, applied at point A here, vertically down. What we've got to do is calculate the magnitude of the resultant force. Now again, if you go back into your notes, what we did was a kind of tabular approach here, where we summated the fx's and the fy's. So in a sort of table we had, and what we would do is work out the x forces and the y forces. Now don't forget, with this force up here, the 20 kilonewton force, we'd resolve that into its x component, we'd resolve that into its y components. That would be the fx for the 20 kilonewton force. This would be the fy for the 20 kilonewton force, and we'd work out the values here using our trig functions, the sine and the cosine functions. And what we would do is eventually add up the forces, summate them here, and we could find from that the resultant force. And that's what the question wants you to find. It wants to find the resultant force here. Now to find the resultant force, what we do is draw the fx force, whatever direction it's drawn in. We draw the fy force, so this would be the summation of the fx's drawn that way. This would be the summation of the fy's drawn that way, and the resultant force would go from the beginning of the diagram to the end. That would be the resultant force, so I call it R, say, or resultant force. So we'll work out the resultant force here. Okay. We also would need to work out the angle, call it angle theta, from the horizontal. So that's the sort of approach we used. Again, I would like you to engage with this to get back into the process, go back to your notes and find out how we actually resolve the forces, how we add them up to get these totals here. We need to find the totals from the tables, and how we work out the resultant force. We basically use Pythagoras theorem. If you go back to your notes, you'll see that R is equal to the summation of the fx squared plus the summation of the fy squared, all square rooted. If you go back to your sort of notes, that's what you'll find. And to find the angle theta, we'll use the tan function. Theta is equal to tan to the -1 of the fy divided by the fx's. So again, I'm going to let you play with that, let you go back and look at that, but that's the sort of things we did to find those resultant force in the angles. All right, so that's just a sort of memory hook to try and get you to engage with that process. The second part of this question was to find the angle. So in this question now we're asked to find the angle, so that is the tan function, angle it makes with the horizontal. So that's the theta value that we looked at here. You're finding the theta value here. So in the first part you're finding the r value, that's the resultant force value. In the second part you're finding the theta value, the angle, okay. And in the third part it wants us to find the moments about point C. So we've got to take moments about this point here. And again, if you go back to your work we did on this, you'll find we worked out the moment in the x direction, the moment in the y direction, and we added the summation of the moments up. So again, I'm going to let you look at that, but that goes back to our table that we looked at in previous calculations. I put it also in the revision sheet in the techniques to remember. I put the table there. It's just quite a question of basically taking this table and extending it to have the mx and the my column. So we sort of just extend that table basically if you look at it, and we will have in here the mx and the my values. They'll be added to the table, okay, and we'll summate those columns as well later on. But I'm going to let you look into how we did all that, because you need to get back into the technique of how to work out the moments. We'll eventually sort of summate both of those, you'll see in the question. They'll actually be totally summated to get the total moment about C, and that's what the question wants you to do. Question 2 relates to friction on inclined plane. That's one topic that we haven't actually covered in any great detail yet. It is in the back of your notes, look in your workbook, it is in the notes there about working out the friction on inclined plane. Basically what they want you to do first of all is to draw a diagram of the forces involved here. So we haven't actually covered this, I said, in the lesson, but if you look in your notes, you'll see that you'll be able to find all the forces acting on the car in this particular case that you can put in a diagram. What you'll find is you'll have a weight force. Don't forget, weight force always acts vertically down. There'll be a weight force acting vertically down. You'll find there'll be a force that's pushing the car up the incline, force P parallel to the incline, and there will also be a friction force associated with the resistance to the motion. So that kind of thing. There's also a normal force here, if you remember from our friction calculations. There's a normal force here. The next question continues with that. It actually wants you to find the maximum frictional force. We looked at friction forces. Friction force was actually forces mu times n, where mu is the coefficient of friction, and it's given in the question in the exam there. But what you need to work out is a normal force, and that normal force is this force shown here on the diagram. We normally use the weight force if it's in a horizontal position, but because it's in an inclined position, it's actually slightly modified from that. And again, the notes show you how to work out the normal force. But that's the formula we use. Friction force is mu times the n there. In the third part, they've given us force P, 3,500 newtons. It's driving the car up the incline, and we've got to find the acceleration. So that's a question of applying Newton's second law, summation of all the force equal to ma, along the incline. Okay, so again, we looked at this kind of thing, working out applying Newton's second law, considering all the forces that are acting parallel to the incline. So again, I'll leave you with that one for now. Quite a difficult question because it involves Newton's second law here. So question 2b, this is giving you a descriptive question, and what you'll need to do is extract the information from the question. You'll give us information about the vehicle's speed it is travelling at. You've got a stopping distance given in the question. You should look at the equations of motion and find an equation that fits the information given, and from that you'll be able to solve for the acceleration. It wants you to find the, in this case, a deceleration to achieve the stopping distance given. Alright, so read the contents of the question. The car is travelling on a horizontal road at a particular speed, and then it comes to rest in a particular distance. We've got to find the deceleration associated with that stopping. And if you go back to your equations of motion, those are the kind of things where you see sort of v squared equals to u plus at, and v squared equals to u squared plus 2as, and there's two more equations that you can look at, and you've got to find the equation that fits the information from the question. And what you've got to do is find the acceleration. They want you to find the acceleration. So whichever equation you're going to use, and that you decide which equation you're going to use, and the 4 it's given, you've got to rearrange it to find the acceleration. That's what that question's all about, really. So again, I'll let you look at that. And the second part of question 2b here, we've got to find the power associated with the car coming to rest. So find the power associated. If you remember, there are equations for working out the power. I think we had two equations. Power was equal to work divided by time, and also power was equal to force multiplied by velocity. So two equations to work out power, but I'll let you decide how you're going to do that given the information in the question. Question 3, this goes back to working out areas and volumes and masses and so on. And again, these are questions I would encourage you to engage with, particularly so centroids and this type of questions are really useful to do. A few marks associated with this, and generally speaking, reasonably straightforward questions. You're given a cross section of a steel beam shown from a structural section. Here dimensions are all in millimeters. We've got to calculate the cross-sectional area of the beam. So the first thing we need to do is to calculate the area, but do notice it says it wants the area in meters squared. So what I would suggest is to put the dimensions in meters first of all. So they're all in millimeters at the moment, but put them into meters and then work out the area of the section. You've got basically 3 strips here. You've got a top strip there, which you can work out the area of quite easily. You've got the web here, and again you can work out the area of that quite easily. And then you've got the lower flange here. You can work out the area of that. So 3 different sections, rectangular sections. You get the geometry for the information as given in the question, and you can work out the area, but you do need it in meters squared. So I would encourage you to put the dimensions in meters first of all, and then work out the area. It prevents you having to convert millimeters squared to meters squared later on. 2 marks associated with that. So once you've found the area, it wants you to calculate the mass of the beam. So they need to give you more information, and they have. They've given you the lengths of the beam, so that will allow you to find the volume. So if you know the area from the previous question and they ask you to find the volume, don't forget that volume is equal to the area multiplied by the length. So the areas from the previous question, and now you've got the length in this question, you can find the volume. And they've given you the density in the question. The density is the 8,000 kilometers per meter cubed. So from that you can find the mass, because don't forget the relationship here, density is equal to the mass divided by the volume. We normally use the symbol rho for density. So density is mass divided by volume, so that's the density value 8,000, which you would have here in the equation. So you can find the mass by rearranging. So I'd encourage you to go for those kind of questions. There's 3 marks associated with them there, and there's 3 marks, relatively straightforward 3 marks really there. So in question 3b here, we're given the beam bending here. We're given some forces applied to the beam. We've got the 14 kilonewton force applied here, a 16 kilonewton force here, but they're giving you the reaction here of 25 kilonewtons and 5 kilonewtons. So you've got reactions. So you've got your 4 forces effectively that are applied to the beam. So like we had in the lesson, these are in kilonewtons. I think we use kilonewtons mostly in the lesson. So 4 forces, if we're doing in red here, that are applied to the beam. And what they want you to do here is not calculate the reactions this time. They're given. Normally they do have to calculate the reaction, but they're given here. They want you to calculate the bending moment diagram. So you need to work out the bending moments, and then you need to draw the bending moment diagram. See the 5 marks here, so it's quite a chunky question. But you're going to calculate bending moments at the A, B, C and D. So if you remember in the notes, we sort of calculate the bending moment A, looking to the left of A, there will be no bending moments to the left of A. Then we calculate the bending moment looking to the left of B, calculate the bending moment looking to the left of C, and calculate the bend moment if you like to the right of D. You can see it's 0 anyway. So you want to calculate the bending moments, okay? So I'll let you have a engage with that and see if you can work out the bending moment diagrams. Question 4 here is a resolution of forces. Again, they give you a context. One of the problems with the OCR questions is that everything is contextualized. You never get anything to sort of just resolve this force. It's always in a context. So in this case, what we've got is a 2,000 Newton load, 2 kilonewton load, if you like, it's acting down here. And the first part of the question, they want you to resolve the force parallel and perpendicular to the jib of the crane, which is this angled part here. So what you'll need to do is resolve the force parallel and perpendicular to that crane. So you have a force sort of here, that'll be parallel, and a force there perpendicular to the crane. Alright, so this will be a sort of right angle in there. So you'll end up with this, they've labelled them as parallel and perpendicular. So sort of the force that's parallel and the force that's perpendicular here. Alright, so that's what we're trying to solve here. It's a bit of trig basically. So if we draw a bit bigger here, you'll have your force down here of 2,000 newtons, and then you'll resolve it into sort of this way and this way. This will be the way you'll resolve your forces here. This will be the right angle in here. The angle is 30 degrees here in the question. You can find using basic trig what the force that's going to be parallel is going to be, and the force that's going to be perpendicular is going to be from basic trig. Alright, so that'll be the sine and cosine functions, but I'm going to let you deal with what they're going to be. There's 2 marks for that, one for... What I want you to do now is calculate the bending moment about the pivot. Now the pivot is shown here. So the bending moment will be generated by the perpendicular force. We'll have worked out the force from the previous work. We'll know what that force is there. So we've got that force there, and they want to know what the bending moment is about the pivot. So it will be force multiplied by this distance across here. They're giving you the distance in the question. It's 2.5 meters. So all they want you to do there is work out the bending moments. This is a force multiplied by its perpendicular distance. So that force is at right angles to the distance there. So to work out the moment, it's simply force multiplied by distance d. This would be the d in this case. There's only 1 mark for that because it's quite a simple calculation there. Okay, we've got to work out the shear stress here. We have stresses for direct stress, stresses for shear stresses. If you remember from your formula, shear stress, I used to use that symbol, is the force applied to the section divided by the area that's in shear. Obviously the shear area will be this area here, which you will need to calculate. Calculate by sort of one rectangle, take away another rectangle. So that's the area that's in shear. And the force applied here, again, that will be, going back to our diagram, that will be the F force here. The F force would be the shearing force that's applied here. So just simply want you to work out the cross-section area and then divide the force by the area, and that will give you the shear stress. They're after the shear stress here. So dividing the P, the applied force, shear force, by the cross-sectional area shown here will give you the shearing stress here. So shear stress calculation. Question 2 is actually a little bit of a descriptive question here. They're actually just asking you to sketch the variation of shear stress and axial stress. It's quite a complicated question, this, in a way. It doesn't want you to do any calculations. It just wants you to sketch it. It's really for people that are going for the sort of distinction type grades here, really, to really understand what's going on here. So they're expecting you to sketch the diagram. If you look at the answer sheet, you will see and the sketches that's involved here. What you would find is as the angle increases from 0, you would find that the shear stress starts to decrease and the tensile stress starts to increase. So your shear stress would kind of be dropping off, and your tension stress would be kind of increasing. So they're sort of looking for some kind of diagram like that, but you really got to understand what's going on there to be able to sketch that. Question 4 part C here, given us a stress strain diagram, and they basically want us to find the elastic modulus value for the stress strain diagram. So the Young's modulus or the elastic modulus value from the stress strain diagram. E is usually the Young's modulus symbol we used, and E relates to the slope of the diagram. So taking 2 points on the line, and then you work out the vertical distance between those 2 points, you work out the horizontal distance between those 2 points, and you can work out the gradient of the line. So that's what they're asking you to find. Find the e-value. The e-value is the gradient of that line here. Okay, there's a descriptive question after that. It's asking you to state what's happening between stresses of 0 and 240 megapascals. So 240 is somewhere up there. Okay, so they're sort of saying what's happening within this region of the stress strain diagram. And again, I'll let you decide what's happening there. Just a sentence that we're looking for. In question 5, part A, it wants you to name an application for a chain drive sprocket, a gear system. I'm sure you can think of an application for that. And in part B, it simply wants you to name the component labelled A here. It's just 1 mark for each of those. What's the name of that particular component? Okay, so descriptive questions there. In part C, it's given us a lever system. So again, this is back to simple machines, looking at levers here. It wants you to state the class of the lever, or the type of the lever. What type of lever? There are 3 types of levers if you look at your system: class 1, class 2, class 3, type 1, type 2, type 3. So you've got to state what type that is. And then it wants you to calculate the minimum value of the input force, sometimes called the effort, required to lift the load that's given in the question. And it also wants you to state the mechanical advantage of the system involved here. So 3 marks here. So sometimes we call this the effort over here. The input force is sometimes called the effort, and the output force is called the load. So this is also called the load, or sometimes called the output force. So load or the output force they want to use. And you'll see in the nomenclature in the OCR formula sheet, they use F in, and I think they use F out in their formula sheet. So again, all these formulae you need, make sure you find them in the formula sheet. They're all given to you, everything you need here to kind of find the mechanical advantage of the system and find the input loads, all given in the formula sheet. It's just a question of picking up the right formula there and then calculating the values. So simple machine still again. Gear train is given here. We're given a direction of gear A. Gear A is shown to be going in this clockwise direction here. We've got to then work out what the direction of rotation is for the other gears. So what's the direction of gear B, gear C and gear D? In the lesson we did this with velocity arrows. If you've got the velocity arrow for gear A, then you can draw the velocity arrow for gear B, gear C and gear D, and you can state whether they're going in the same directions or different directions to gear A. So again, I'll let you think of that. Only 1 mark there because it's a relatively straightforward question. But velocity arrows sometimes help when you're drawing these diagrams. And then continuing with the question, part 2, we're told that gear A rotates at 800 RPM. We've got to calculate the speed of the output gear, in gear D in this case. So you're given a number of teeth in the question, and you'll need to know the number of teeth to help you calculate the overall gear ratio, the velocity ratio for the gear system. So again, I'd encourage you to use the formulas in the formula booklet to calculate the speeds and the gear ratios. It's all really driven by standard formulas there. We're given the number of teeth for gear A, of course, as well there. And don't forget, we sometimes call the velocity ratio the gear ratio as well. So just be aware of that. Sometimes it's called the gear ratio as well. So just be aware. And don't forget, we sometimes call the velocity ratio the gear ratio as well. So just be aware of that. Sometimes it's called the gear ratio as well. So just be aware. Okay. And then question 6, I think is the last question we're going to look at. This goes to dynamics and looking at energy methods. These are quite complicated questions. You remember in the lesson, they're quite difficult questions. You're given a scenario here. So what they'll be looking at is trying to calculate things like potential energies, kinetic energies and work done, working around the system here. So the context is a skier having a mass of 80 kilograms, starts from rest. Again, you need to be aware of that. Rest is 0 velocity at point A. So they start up here at point A. One of the questions, we've got to calculate the loss in potential energy as the skier travels from A to B. So when the skier is at B, which is 12 meters above a datum, we've dropped from 20 meters. So that's how you calculate the potential energy. Again, if you go back to our notes, one of the key things we needed to do for calculating potential energy was have a datum in our system, and then you can work out the change in height, and from that you can work out the loss of potential energy in the system. So 1 mark for doing that. And then we're given that the work done against the resistance between points A and B is 2000 joules, and from that we've got to calculate the speed that the skier has at point B. So these are quite complicated questions here. So sort of an energy balance is required here to rearrange the equation, and then you'll be able to find from that the velocity. Alright, so thinking in terms of energy, think of what energies you've got to begin with and what energy you've got finally, and from that hopefully you can work out the velocity. Okay. But if you go back to your notes, you'll see we did an awful lot of work on these kind of things. I think the scenario we had in the lesson, if I remember rightly, was a fairground ride. I think it was a roller coaster ride, and this is really a similar kind of thing. This is a skier on a ski slope, but it's a very similar context to what we had before. The question continues here. We're asked to calculate the horizontal velocity and then the distance travelled in the time taken. So again, you need to read the question carefully here. You'll need to use a little bit of trig to work out the horizontal velocity. The previous question would give us a velocity sort of in this direction, and we got the velocity, find the velocity in the horizontal direction, so that's the velocity we'll be using. So we need to use a bit of trig here to find the velocity in the horizontal direction, and then from that we can find the distance travelled. Alright, so again, quite complicated questions these, more difficult questions. Question B wants us to calculate the final velocity of a chairlift. So we've got it's a sort of momentum, this one. So the chairlift ascends to the top of a slope. Chair has a mass, we've got the mass there, and it's travelling at that particular speed before the skier sits in the chairlift, and then the skier is stationary before sitting in the chair. And using conservation of momentum, we've got to determine the combined velocity of the skier and the chair immediately after the skier sits down. So the context is totally different to what we did in the lesson. In the lesson we had things like cars impact on each other, that kind of thing. This is really a person on a chairlift, and then we're finding the resultant velocity after the impact. So a very clever little scenario that OCR have used here, but it's all based around this momentum equation, the m1u1 plus m2u2 equals m3v3. Okay, so again, I'd encourage you to get back into your momentum notes and see if you can extract the information from the question. You need to know what the m1, the m2 is, and then the u1, u2 is, and you've got to eventually find the v3 of that equation in that one. And then finally, question 2 of the question, again, is going back to the context of the chairlift. They've given us this loading system here. We've got some loads applied to the system. We've got a uniformly distributed load across the seat here. This is the actual chair. We've got a point load applied of 2000 newtons. We've got to work out what the supporting cable forces are. So in other words, we need to find the cable forces over here. If I call that P there, call that P. We've got to find what the value of P is going to be in the cables given the load is. You need to understand how to deal with a uniformly distributed load like we did in the lesson, and then split that load equally between the two supporting cables, and the same with the point load here, split that equally between the two cables. So fairly straightforward question really if you understand how to deal with the UDL loading. And that's it, that's the end of the question paper.